So let me show you what I mean. Let's talk about related rates. 2.6. Let's go solving related rates. Solving related rates. So when you're solving related rates, what you will do, you're going to first find an equation. An equation relating to pieces of information, to variables. Sometimes or more. Two or more variables. You're gonna have an equation like the area equation of a circle. Area of a circle relates to the radius of a circle. Right? That's an equation relating to variables. Or the position of a rocket depends on the exhaust speed of a rocket. Right? Those are two variables relating each other. You're going to find an equation relating these two, sometimes more variables. Right? It's like a rocket speed not only depends upon the exhaust velocity, but also the mass of the rocket. So sometimes there's more variables involved. But there's always at least two variables, and you find an equation relating those variables. Second thing you're going to do is find a derivative. Usually with respect to time. So it's going to be d dt. Usually, when we do related rate problems, the rate we're talking about is related to time. A change in radius with respect to time. The radius is growing a certain amount every second. Or you are pumping air into a balloon at a certain volume per minute, or whatever rate you're talking about. So you do a derivative, usually with respect to time. For these related rate problems, you find this equation, you take your derivative with respect to time. And for 3, you're going to plug in some initial condition. Initial condition of the state of the situation. So you'll be given some information. You'll be given this information. This is given. You'll be told at this moment in time, after 3 minutes of time, the radius is this big. The rate is one of the rates is this much. You'll be given some initial information of the current state of the situation you're talking about. Some variables, you will know some information. And you're going to plug that information into the derivative equation that you get and solve for the part that you don't know. Solve for the unknown. Plug in some initial condition of the state of the situation. And that information will be given to you from the problem. So we're going to do some examples. We're going to talk about different types of situations that happen. And again, I'll give you this information quickly so we can get out of here. So for example, so you're going to get an equation. You're going to find the derivative, usually with respect to time. You're going to plug in some initial condition of the information and solve for the unknown. So I want to say for this problem, we're going to say solve for dy dt given dx dt is equal to 2 when x is equal to 1. So this is some information, and here's the problem here. Y equals x squared plus 3. X squared plus 3. There's our equation. There's our situation. Given this information, and we want to know what is dy dt. What is dy dt? When we're given that, we want to know the change of y with respect to time. Given that x is changing 2 amount per second, or 2 whatever per something, at the moment when x is equal to 1. So this here is our given information. This is the rate of change of x, this dx dt. And you can think of x equaling 1, this is like the current moment. Right? So we know some given information. We have like a snapshot of some moment in time. The moment when x is equal to 1, we know that the rate of change of x is equal to 2. So we have this snapshot moment. We're going to use this snapshot moment to plug into our derivative, to plug in the information, and then we'll use that to solve for dy dt. And this is how related rate problems happen all the time. You're given some state of information, some state of the situation, and you use that information to plug into dy dt, to plug in to solve for dy dt, or solve for the unknown. So this is a real basic example. Let's do this real basic example together. Plug in this information, right? The rate of change, we're given the rate of change of x, how much x is changing, and we're given like the current moment in time when x is equal to 1. So the first thing we're going to do is take our derivative with respect to t. We do ddt of the whole problem. So we do our implicit differentiation with respect to t. So we're going to get dy dt, the derivative of y with respect to t, our rate of change of y in terms of time, how quickly y is changing, and this is what we want, dy dt, equals, so I'm doing my derivative of x here with respect to t. So I'm going to have to use my little chain rule thinking and do my derivative of x. So I have my power rule here with x. I've got 2x. And then I have to remember that I need to also multiply. Since I'm doing the derivative of t, I'm going to have a dx dt piece as well. I'm going to have this dx dt because we're doing a derivative with respect to t. So we have this, right, this chain rule situation where I do the outside part, the 2x part, get that times the derivative of the inside, the x by itself, gets its own little derivative because it's a dt. If we were doing the derivative with respect to x, this would be dx over dx and would disappear to a 1. But we're doing it with t. We're doing it with respect to time. So we have to put dx dt there as well. And then the 3, any derivative of a constant goes to a 0. So that's just 0 from the 3, so that's gone. So this is our equation of dy. Oh shoot! When I put dy dy, no. Dy dt. Sorry, everybody. Dy dt. This is our equation here. Dy dt equals this sort of problem, this situation that we're running into here. So now that I have this situation, I have my equation. I did my derivative. right? I found the equation, I did the derivative. Third step, plug in your initial conditions, plug in your state. So I have here dy, dx dt is 2, and x is 1. So I'm going to plug those, plug those into this situation here. So I'm going to say equals, equals 2 times dx dt, well, x is 1, and dx dt is 2. So 2 times 1 times 2, that would be 4. So dy dt is equal to 4 at this moment in time. When these conditions are present, my rate of change of y is 4. So that's an example of the kind of problems that we'll do, right? We have some equation, we have some initial condition, do your derivative, find the initial condition, set those up, plug in the problem, and get your missing answer. Okay. So this is an abstract example of what that looks like. Just a y equals x equation given some random information. The part that's missing in all of this, the part that's missing in this equation here, is the units. We don't understand what we're talking about. There's no real life application to this. Like, it doesn't describe any particular thing. And the important thing about related rate problems is they give examples of real situations. Units are important. When you are doing related rate problems, you really need to think about, you need to pay attention to the units that the problem is talking about. Important. Units are important. Are we talking about meters per second? Are we talking about area, square feet per hour? What's the units that you're talking about, and where do those get plugged in, and how do we understand what those units are? So let me give you this example, another problem where we're going to involve units and involve related rates. So let's say that a pebble, or a rock, pebble, a rock, is dropped in a pond, dropped in a pond. So we have a rock here, gets dropped in a pond, right? Splash. Bloop, bloop, bloop. What's going to happen is it's going to develop little concentric rings, right? These are ripples, right? Ripples in the pond. It's going to, right, ripple out of the pond. And those ripples are going to have a center and some radius that's going to be growing as the rings expand. Radius grows as the rings expand. Right, the ripples go out from the center of where the rock gets dropped in a pond. So the radius is going to grow as those ripples expand. And it's going to grow at a rate of dr dt. It's the rate of growth of the rings, right? The rate of expansion, how fast that radius is moving through the water, how quickly it's growing. And we're gonna talk about this unit in terms of feet per second. It's growing at some rate, dr dt, in feet per second. So now we're looking at a real situation where we can look at a physical object and understand what's changing about this physical situation. Something that's changing is the rings are growing, and the radius of the rings is shooting outward as the rings expand, right? And this is why derivatives, like what I mentioned, derivatives are a calculation of change. Derivatives help us to calculate change. And so when you're thinking of a situation, think about what is changing about the situation, what is measurable about the situation. How can I break this situation down into simpler pieces? And one simple piece about this ring is the radius of a ring, right? Circles and radiuses, right? All that stuff. So we have a situation. We're going to give some initial conditions here. We're going to say the radius of the outer ring is growing at 1 foot per second. The radius of the outer ring is growing at 1 foot per second. That's our given information. The question is, find the area, find the, I should say, let me ask it a better way. When the radius is 4 feet, it's 4 feet long, what rate is the area of the ripple growing? So here is a kind of related rate question. So you drop a rock in some water, the ripples stream out. We know the speed of the ripples are growing at 1 foot per second. The question asks, it tells us the radius is 4 feet, so we have a moment in time. At that moment in time, at the 4 foot long radius mark, when the radius hits 4 feet long, how quickly, at what rate, is the area of the ripples growing? At what rate is the area growing? So we need to come up with what equation do we need? What initial information do we have? What equation do we need? What initial information do we have? And then take our derivative to solve and plug in. So we need to break down this process into these steps. So our first step, find an equation. What equation are we going to use? What equation relates these two variables of area? I need to know my area and my radius. That's the information I want to find, right? I want to find area. So what equation are we going to use in this situation? We're talking about area. These ripples are on a flat surface. What equation can find the area of these concentric rings of this like ring of water. What equation are we going to use? Who has an answer for me? What equation might we use when doing this problem? We want to know the area of these rings on the surface of the water. What equation of area might we use? Who's got an idea? Exactly. Right, Jennifer, exactly. It is a circle. These rings are a circle on the surface of the water. So the area formula for a circle is pi r squared. So that's our formula. The area of the rings is equal to pi times the radius of the ring squared, right? That's the situation we're in. This is not like a sphere, a ball. We wouldn't need those formulas. This is not like a cone shape where we have a bunch of area formulas of cones. This is not like some kind of weird prism shape. We got circles here. So we use the formula for circle. This is not a cube. So you got to remember all the formulas way back in geometry that you had information of. You got to remember all those formulas. Oh, this is a cone. What's the area formula for a cone? Oh man, I don't remember that at all. It's been way too long. Formula for a cone? I'm never going to remember that. Formula area for a sphere? I don't remember the formula for the area of a sphere. What about the surface area of a sphere? No way. Nice thing about the AP test. They are going to give you many of these area and volume formulas. They're going to give you many of these formulas. So you won't have to rack your brain too much. But it's always helpful to have them in your mind so you don't have to go looking for them later. So if you can memorize these formulas, then I'll be giving you a page full of formulas of various areas and volumes. You'll be getting that too. If you can use that and like remember these formulas, that's going to help you out quite a lot in these kind of situations. So we have our area formula, we have our equation. Great. What is our initial condition? Or I should say just maybe the conditions. What are the conditions we have? What information do we have? Conditions. What do we know about the situation? It tells us a few things. It tells us that the radius of the outer ring is growing at 1 foot per second. So this is dr dt. So we know that dr dt is 1 foot per second. Given us that information in the problem. And we want to find the area. We want to find the rate of area. This is dA dt. This is what we want. What rate, right? That's looking for, it's telling us we are looking for dA dt when the radius is 4 feet. So here's another piece of information. We have here that r is 4 feet. So we want to find dA dt when r is 4 feet. Those are our initial conditions. That is what the problem is asking us to do. So you see how, right, we're looking for this area, we're given this radius. Those are our related variables. Those are our related rates. And they connect with this area formula. All the pieces that you have should be included in the formula for the area. If they give you some information, you're going to have that information in our equation. given the conditions, given the situation, all of these pieces connect together. Looking for an area, so we want the area formula. Okay, that's a clue. Using the area formula, I know it's pi r squared. So I'm going to have to do something with r. Let me look at the problem. There we go. It tells me about dr dt, and it tells me the r value at the time. So we're going to use those pieces. That's our initial conditions. We're going to plug in that information and solve this. Okay, so now that we've got all that gathered, we're going to do ddt. Find our derivative. ddt of my area formula equals pi r squared. Do my derivative. So I'm going to get dA dt do my derivative, dA dt, and then the derivative of pi r squared, I'm going to do my power rule, bring the 2 down in front, so it's 2 pi r, and then I need another times dr dt, because my chain rule, I'm doing the derivative with respect to time. So radius has a derivative, the r has a derivative dr dt. There is the equation I can use to get my derivative of area. There's that piece that I'm looking for. I want to find dA dt, find the rate of change of area. Here's my area formula. I do the derivative, got my 2 pi, bring the 2 down in front, 2 pi times the r times dr dt, because I'm doing a derivative of the r with respect to time. I'm doing the derivative of this thing with respect to time, like we had a implicit derivative. Same thing with like implicit differentiation. The dr dt comes from the derivative because of ddt, right? So the r has a derivative as well, because it's derivative of time. So maybe I can call this, oopsies, maybe I can call this like solve or derivative or something. I'm doing the derivative with respect to time, right? We do the derivative ddt, so we get dA dt, the derivative of area with respect to time, equals, right? Do the derivative of this, the 2 goes in front, 2 pi r, and then the derivative of r dr dt implicitly. So now I've got this formula, I've got my information, I got dr dt right there, I've got my radius is 4, so plug those in, and I'm going to get 2 pi times 4 feet, 4 feet is my r, times 1 foot per second. So my answer here, let's see, 2 times 4 is 8, times 1 is 8, 8 pi, and what are my units? What units am I going to get? Well, I've got feet times feet per second. Feet times feet is feet squared per second. Exactly. Which is correct because this is an area. Area over time, right? Derivative of area per time. Area is square feet. Square feet per second. That is the rate of change of this area of my ripples through the water. They are growing, because this is a positive rate, growing 8 pi square feet every second. That's how much bigger they are getting, the area is getting every second. 8 pi square feet every second, 1 1,000, 2 1,000, 3 1,000. It's adding 8 pi square feet of area. at 4 feet adds another 1 more second. It adds another 8 pi square feet. 1 more second adds another 8 pi square feet, right? So the area of the circle, of the ripple, is growing, oh goodness, growing at a rate of 8 pi square feet per second when the radius is equal to 4 feet. Okay? You okay with that? I do want to do one more example about a balloon. Right? So you find the formula, you find the derivative, you find the initial conditions, and then you plug them in and you find the missing part. Parasite is napping right now with his mother. But yeah, we'll do one more example. I want to do one with volume. So here's another example. Let me do one more. See how I can do this quickly before we get to that 7 minutes of terror. All right, let's do the volume of an inflating balloon. Is balloon 2 L's 2 O's? It's a balloon. Yes, balloon. Excellent. So, let me tell you here an example. Air is pumped. Air is pumped into a balloon at a rate of let's go 4.5 cubic feet per minute. Oops, per minute. Cubic feet per minute. I want to find the rate of change of the radius when the balloon is 4 feet across. So let's examine this. Got a balloon. Here's a balloon. Air is being put in the balloon. 4.5 cubic feet per minute. Air is being pumped in. I know that the balloon is, let's go here. The balloon is 4 feet across. And I want to know what is the radius. I want to know what dr dt is equal to. So let's break down some of the pieces of information we know. So we're looking at volume, right? Looking at volume. And we have a balloon, which is basically like a ball, right? Balloon volume, that's a ball. So this 4.5 cubic feet per minute, this is the change in volume in time. That's dV dt, right? 4.5 cubic feet per minute. Cubic, right? That's units are important. They tell you a lot about the situation. If we're doing cubic feet is a measurement of volume. So we have dV dt telling us volume. It wants us to find the rate of change of the radius. So we want to know dr dt is unknown. And it tells us that the balloon is 4 feet across. So this is telling us maybe like the radius of the balloon. If it's 4 feet across, what's the radius right now? Well, 4 feet across, that's the diameter. Radius is going to be 2, half of the diameter. Radius is 2. Right, so you're breaking down this situation. You get the change in volume over time. What you're pumping into the balloon is 4.5 cubic feet per minute. So we have volume, we have radius. Let's think of what equation are we going to use? What equation are we going to use to solve this problem? What's the equation that relates volume and radius? Well, again, it's a sphere. It's a balloon. We're talking about around like a spherical balloon. And so we use the volume formula for a sphere. If you don't know it by heart, I'll tell you. Volume of a sphere is 4/3 pi r cubed. That's the volume of a sphere. One of those formulas that will be very helpful for you to have memorized. 4/3 pi r cubed is the volume of a sphere. Second, let's break down what we're given. We are given the change in volume. We know how much air we are putting into the balloon. It's 4.5 cubic feet per minute. Whoop, what happened? What happened here? What am I doing? There. We were given the change in volume over time, 4.5 cubic feet per minute. That's our volume, right? Like we're blowing up the balloon. How much volume of air you're inputting. We want to find dr when the radius is equal to 2, right? It says 4 feet across, but keep in mind, 4 feet across, half of that is the radius. So don't be tricked by that. It said find the rate of change of the radius, find dr dt. Find the rate of change of radius. What's happening with the balloon? is, goodness gracious, ignore my handwriting, everybody. We got our information, we got our volume, we got our formula. Let's do our derivative. Solve this. So I'm going to do d dt of my volume formula. V equals 4/3 pi r cubed. Do the derivative. Now that we got all the information from the problem, do the derivative, let's solve it. This is dv dt equals, got to do my derivative. My derivative here, I use my power rule again. The cube goes down in front, and actually this 3 is going to be really nice. It's going to cancel the 3 on the bottom of the fraction down here. So I move it in front, it's going to just really cancel that 3 there and become a squared. So I'm just going to write this is 4 pi r squared, and then I need my dr dt. Don't forget your second implicit part. Don't forget the r needs a derivative too. Okay? Good with that so far, everybody? Take our derivative with respect to time. dv dt equals 4 pi r squared dr dt. Now that we have our derivative, right, that process is done, we simply plug in all the known information. dv dt I know is 4.5. 4.5. I know this is 4 pi. I know that r is 2, so this is going to be 2 squared dr dt. And I am now going to solve, this is an algebra problem. I'm going to solve for this, solve for dr dt by itself. So let's see. 4.5 equals, let's see, 2 squared is 4. 4 times 4 is 16 pi dr dt. And I'm just going to divide by 16 pi on both sides. Divide by 16 pi on both sides. And we're going to get dr dt is going to equal, let's see, (4.5 over 16 pi). What unit is this going to be? Or it's about 0.09. But what units is that? What's our units? Change of radius over change in time. What units do we have? Well, we've got cubic feet per minute. We have our radius is 4 feet across, so the radius is 2 feet. So we have feet cubed per minute, and then radius is feet. So what units am I changing my radius, dr, the radius unit? Radius is in feet. Radius units are feet. Okay, the radius units are feet. The time unit, the dt part, well, in the volume, this was in cubic feet per minute, right? The dt part is the time part. And I think, what time am I using so far? In the problem, the only time I've got was the per minute. So my units of my radius are going to be in feet per minute, because it's a rate, it's a dt. The minutes part comes from the dt, and the feet is from the radius, the dr, right? So these are our units. Really important to remember how to coordinate those units to look at the problem and see what units are going to be left over. Well, we had 4.5 cubic feet, 16 pi is square feet. Cancel those, we've got 1 foot left, and there's per minute, so it's feet per minute. Change in over change in time. What measurement, what units are we talking about? And so I will write down here, never forget the units. In the AP test, if you do not write the units, you will lose a point on the free response questions. Multiple choice, they don't care. But free response, you need to write down the units. They will require you to have that part of your answer. So in these problems that I give you, never forget the units. Practice these questions. Use all the units. See if we can make sense of things. Look at the problem again. Think about what am I measuring? The radius. What unit was the radius in? Radius was feet. Okay, radius was in feet. Give me feet. So it's feet per time. Per time. What's the time measurement we have here? Time. Look through. You see. Oh, that was minutes. So my units have to be 0.09 feet per minute. So look through the problem. Check out the units. Make sure you got all that. Any questions about this thing here? Making a little sense. Get your equation. Set up your equation. Find the given information. Take the derivative. Plug in and solve. These first two probably are the most difficult, challenging parts. But the equations that you need are all going to be handed to you. And again, I'm going to post a handout with a bunch of different formulas for volumes and areas and things like that. We're going to have a lot of practice doing volume formulas in this section. All right. So let's end it. Homework. Section 2.6. Page 157. I want you to do numbers 3, 5, and then 11 through 15 all. Those are your questions. It's like 7 questions. 2.6, page 157, 3, 5, and 11 to 15 all. Practice finding the formulas, practice finding the units, practice doing your derivatives. And we'll get more into this. This is solving related rates. That's the title of these notes, solving related rates. I also wanted to mention, everyone, would it be helpful? I know that we didn't have our study session this week on Wednesday. I was occupied. But would it be helpful? Do you want to do it tomorrow, or should we wait till next week? I can do a study session tomorrow. We can do the homework together tomorrow. Or would next week be fine? Next week on Wednesday. Let me know. We can work it out. Next week's okay? Okay. You know what? I'll offer it tomorrow if, well, no, I don't know. I don't want to do that. If next week is better, we can just do it next week. That's fine. We'll go over this next week anyway on Tuesday. So we'll review it then. All right, everybody. Great. Well, thank you. Let's check out the space thing now. We got a couple minutes.